Hi everyone. So today we will solve this problem, nearest exit from entrance in A. So we are provided with a m by n matrix, and each cell has either value dot or plus. So dot represents an empty cell and plus represents a wall. And we are also provided with the entrance. So this is a vector which contains two values, row and column. So this row and column basically represents a cell inside this matrix from where we have to begin our traversal. Okay. In this matrix, we can move in four directions: up, down, left, and right. And we cannot go through a cell which has, and we cannot go through a wall, obviously. And what we have to do is we have to get out of this maze in minimum number of steps. Okay, so we have to tell how many minimum number of steps will it take to get us out of this matrix. Okay, so in the first example, if we see, this is the entrance. Okay, from where we should begin our traversal. And how can we get out of this matrix? So if we reach a cell which is at the border of the matrix, so such cells are these, correct? So if we can reach any one of these cells in the shortest time or the shortest path, that means that is our answer. Okay. So now suppose I want to reach this cell, correct? So I can move from here till here with one step, then I can move to this cell with the second step. That means I can get out of this matrix via two steps. Okay. Or what I can do, I can try to reach this cell. So I can start from here and in one step I can go to this cell. So to this cell, we reached in a single step, which is smaller than 2. So our current answer will be 1. And if we look at this cell, we cannot reach this cell from any direction because we cannot move diagonally. We can either move in this direction or bottom, which is not possible. So this cell is basically enclosed, so we cannot reach this cell. So our answer will be 1. So in single step, we can get out of this matrix. So this is what we have to calculate over here. So let's look at the algorithm to solve this problem. All right, so let's look at this example. So on the left hand side, we have a matrix, and on the right hand side, we have a representation of this matrix in graph format. So that means what we have done, now we have converted this matrix problem to a graph problem. So the graph problem statement will be that we are provided with a source and we have to reach the destination in the shortest path, right? And in this scenario, there are multiple destinations. Okay. So all these nodes which are at the border are our destination nodes. So to solve this problem, we will be using BFS. Why? Because whenever the weight of the edge is not given or it is same, in that scenario, when we apply BFS from a source, it will always reach destination using shortest path. Okay. So that's why we will be using BFS in this scenario. So what we have to do, we have to apply BFS from this source. And whenever we reach any of these border nodes, A, B, C, H, G, E, okay, we will stop and we will just see how many steps did we took to reach here. And we will simply return that answer. Okay. So let's apply BFS on this. So we are at the source. So first we will push source. And how many steps did we took to reach source? It is 0 for now because we were at the source, right? Now what we will do, there will be a loop which will check if queue is empty or not. So queue is not empty. So we will extract this source and delete it from the queue. And we will push the neighbors of this source S. So the neighbors are D and F. We will push D and then F. Okay. There is no other neighbor because on the left and the down we have a tree. Sorry, not tree. We have a wall. So we cannot traverse that node, right? And how many steps did we took to reach D and F? We can simply add 1 to the previous value. So previous value was 0. So we will simply add 1. So to reach D, it took 1 step. To reach F, it took 1 step. We can verify from the graph also, right? And then again, we will check if the queue is empty or not. Queue is not empty. So we will remove the element from the front, that is D. And again, we will push the neighbor of D. So there is only a single neighbor of D, that is B. So we will push B. We cannot push S again. Why? Because S is already traversed. So we cannot push a node which is already traversed, right? So this is it. Then we will store how many steps did we took to reach B. We will simply add 1 to the previous value of D. The previous value of D is 1. 1 plus 1, 2. So it took 2 steps to reach B. Also, we know that this B is on the border. That means B should stop and we should simply return this 2. So this is our answer. We have reached the border in the shortest path. Okay, using this shortest path. So this is our answer, right? So this is when we stop and we simply get out of the loop and the algorithm is done. So let's try to code this. All right, so let's look at this code. So we have created a queue because we want to apply BFS. And if you see, this queue can store a element of pair. Okay, so we have a pair, and inside this pair also we have 2 values. First is pair and second is an integer type value. So this pair basically represents a particular cell. So we know in a matrix to represent a cell, we need 2 values, row and column, right? And in this pair, the first int represents the row and the second int represents the column. And in this pair, the second value represents the amount of distance we took to reach a particular node, right? So this is it. This is our queue. Then we have this source pair. Okay, so here also to represent the cell in a particular matrix, we have 2 values. Okay, first row and then column, and this third value basically represents the amount of distance it took to reach that particular cell in the matrix, right? Then this is maze row and this is maze column. Then we have this entrance. So the first element of this entrance is the row and the second element is the column. So entrance 0 represents the row and entrance 1 represents the column, right? So we will store it in a source. So the first element of this source, which is this first and second, these 2 stores the row and the column of that entrance, and the second member of this source stores the amount of distance it took to reach this particular source. So since we know that we are at the source right now, so it took 0 steps to reach there. Okay. And we have also created a vector of pairs. Okay. So if you see in this direction vector, each element has values like 0, -1, -1, 0. So if you add 0, -1 to any cell value, we will move left, correct? Because suppose cell value is 2, 3. And if we add 2 with 0 and 3 with -1, what we will get? 2, 2. That means we moved left side. Similarly, here if we see, if we want to go to the top, that means we should reduce the value of a row by 1. So that's what we are doing. If we have a row as 5, 2, if we have a cell as 5, 2, then the row is 5. So we need to reduce it by 1. So we will reduce it by 1 and the column will remain same. So that's why it is 0. So this is just a representation, okay, so that we can traverse or we can look in 4 direction in easy way. So in the beginning of the BFS algorithm, what we do, we push a source to the queue. That's what we have done. And we will mark this source as visited. Okay. So we are marking a particular source as visited inside the maze itself so that we can save some space. So we will mark it as plus because we know we cannot access any cell which has plus. So that means we cannot access this particular source anymore, correct? So that's why we are marking it as plus. Then we will check and this loop will keep on running until this queue is empty. So first of all, we will fetch the front element which is in the queue for queue.front, and then we will remove that element. Then what we will do, we will fetch what is the row and the column of the source, because this current contains many information. It contains the amount of distance it took to reach. It contains the row and the column. Then what we will do, we will check if we reached border or not. As we know, whenever we reach border, we don't have to do anything. We will simply get out of the loop and we will return current dot second. This is the current distance it took to reach this particular source, okay, or this particular node. So that's what we are checking, but that is not true for the source. So what we will do, we will look in the 4 directions. So if you see, we are running from 0 till 4. We are running this loop on this vector, correct? So what we will do, in each iteration, we will calculate row and column based on the values inside this direction vector. So sometimes it will be r minus 1, sometimes it will be column minus 1, and vice versa, right? And it will produce all 4 directions. So when all 4 direction is produced, we first need to check that we should not, like it should not be smaller than 0. It might be possible that we are at row number 0, and if we are looking at the left, so 0 minus 1 will give us minus 1, correct? So in that scenario, we should not look at the element or any cell which is outside of the matrix. So these are the condition which will stop it. Okay, so if you also see that we have also put this condition, we can only access any element which is dot. If it is not dot, we cannot do anything. So once these conditions are fulfilled, that means whatever the neighbor we are looking at, it is inside the maze, it is not at the border, and it is not a plus, right? And then we will push it inside the queue and we will mark it as visited. Okay, so this iteration, this loop will keep on going, and at some point of time, we will reach a border element and we will return that current dot second. One thing to notice is when we are pushing element to the queue, this part basically represents the cell, and this represents the distance it took us to reach that particular cell. Because suppose to reach the current node which we removed from the queue, we took 5 steps. So to reach our neighbor, how many steps we will take? 5 plus 1, correct? So that's what we are doing here. This is the current node, and to reach the neighbor, we will take current dot second plus 1. So this is the code. I will share the link to this code. You can access it. Thanks for watching the video. Bye. Take care.